Good morning. Welcome to the Romax Technology Dynamic Fusion in Action webinar. Thank you for joining. I'm Rahini Sayal, Romax Marketing Campaign Manager, and our presenter today is Dr. Michael Platten, NVH Specialist and Product Manager. The presentation today will approximately last 35 minutes, including a question and answer session. Before we get started, I'll just give a little bit of background of Romax Technology. We're an integrated software and services company for gearbox, bearings and driveline systems for the automotive, aerospace, bearings, off-road, rail, marine and wind engine industries. For over 25 years, we've been providing consultant engineering support services. Our revolutionary software tools are Romax Designer, Concept, CAD Fusion and DynamicFUSION. We provide drivetrain design analysis software tools used by 14 of the top 15 automotive OEMs. Our right first-time approach is used to solve engineering and process challenges you face and to accelerate your design and development cycles. Customers can achieve concept, detailed designs for analysis, validation, testing, and measurable and sustainable end-to-end process improvements. Let's get started. I'll now hand over to Michael and let him giving you a full overview of Dynamic Fusion in Action. Thank you.
Good morning, everyone. Thank you, or good afternoon, good evening, wherever you are in the world. And thank you, Rahini, for that introduction. So today's webinar is on Dynamic Fusion in Action. For those of you that have not seen Dynamic Fusion before, I'll be giving a brief overview of Dynamic Fusion. You can find a lot more information about Dynamic Fusion on our website in the software section of the website, so please take a look there for more details, but I'll give you a catch-up here to make sure everyone's up to speed. And essentially, Dynamic Fusion is a product from Romax Designer which allows you to take a Romax Designer model or a concept model and convert it into a multi-body model, which you can then simulate various transient, nonlinear NVH phenomena within a gearbox and driveline. After that, we'll go into the case studies, and I've got two case studies here today. One is looking at how we can use this to look at gear rattle simulation using tools outside of Romax, and we'll be looking at examples using the Modelica translator in Dynamic Fusion and also the Adams translator in Dynamic Fusion. Case study number two is very interesting. This is a simulation of whole vehicle drivability, and this is in collaboration with our partners at Gamma Technologies, who produce the GT Suite software, and we'll be looking at how we can use Dynamic Fusion to insert a model of a transmission into a whole vehicle model for dynamic simulation. So here's a quick overview of what Dynamic Fusion is and what it does. As I said, Dynamic Fusion, its purpose is to create multi-body dynamic models of gearboxes, drivelines, whatever you have created in your Romax Designer or concept models. And critically, these models are optimized for their speed and accuracy. By speed, I mean their speed of simulation. Once this generic multi-body model is created, you can then translate it into a format that you can use to simulate in other popular commercial codes. The two translators we provide at the moment are for Adams and Modelica format. Adams, of course, is the 3D simulation tool from MSC that's very well known and widely used throughout the world. Modelica is a multi-domain, multi-physics simulation tool which can be used to simulate a number of different things, such as not just mechanics, but hydraulics, electronics, control, and so on. And also, crucially, we also provide the information in the multi-body model in a form that you can use to translate it yourself, and that's exactly how we've been working with Gamma Technologies and GT Suite with Dynamic Fusion, as you'll see later. Once this multi-body models are created, it allows you to create them very quickly. You can go back and edit your Romax Designer model to make changes and then recreate the multi-body model. And these are going to run faster and be more accurate. And this means that we can start to look at driveline transient simulation phenomena, things like clunk and shunt, drivetrain rattle, drivetrain resonances, this kind of thing, as you'll see later. Critically, we can start to do this very early in the development cycle. So we can design out problems with driveline dynamics, begin that process right from the start. So by the time we come to the final design, we have our right first time design. So there are three fundamental problems with multi-body dynamics that make it difficult to use in these circumstances, and these are the problems that DynamicFUSION has been designed to address. Problem number one is that, as any of you who create multi-body models will know, multi-body models take a long time to construct, and they're difficult to edit when you need to reflect changes to the design. So how does DynamicFUSION provide a solution to this is that, of course, we're generating these multi-body models automatically from an existing Romax driveline model, which is, of course, parametric. Many people will already have this model. If you're a user of Romax, these models will already be in existence. And so it's easy for you to do that. But, of course, Romax software is designed specifically for building models of transmissions and drivelines, so it's quicker to do than in a generic multi-body code. Problem number two is that depending on what we are trying to model, ideally you need to have different levels of detail in your multi-body model. Some, for example, low frequency type problems, you need a relatively coarse model. In fact, you may only require something of the level of a kinematic model to perform your simulation, for example, for a control system. Whereas for something more involved, such as a rattle problem or a clunk problem, higher frequency problem involving higher frequencies, you need a lot more detail in your model to be able to do that. And so that means, as a multi-body user, you've not just got to create one model, you've got to create several models at different levels of detail. So with DynamicFUSION, the solution is, because it's so quick to do this, we can do that very easily. We can create many multi-body models, different levels of detail, simply by inputting the required frequency range that we're interested in, depending on what phenomenon we want to investigate. And then finally, problem number three is that there is always a balance when building a multi-body model, a trade-off between the accuracy of the model and the solution time. Basically, we want to minimize the number of equations that the circuit computer needs to solve, minimize the number of degrees of freedom, but still maintain the degree of accuracy that we require. And when you have to create many different multi-body models at different stimulation levels, that becomes difficult. The temptation is to build a simple model because it's easier to build and because it will run very quickly. But that may mean that you're ending up with results that are not accurate enough. So the solution, as I said in DynamicFUSION, is to automatically optimize the discretization, that is how the model is chopped up into the individual bodies in the multi-body model, in such a way that we maximize the accuracy of the model while minimizing the number of degrees of freedom and hence reducing the simulation time. So once we have this model that's been translated in DynamicFUSION into a multi-body form, it's just in a generic form. We need to be able to translate it into forms that other software can recognize, so of course we can actually simulate it. Modelica is one of those translators. As I mentioned, Modelica is a multi-domain, multi-physics simulation tool. Typically in mechanics, you're only simulating here 1 degrees of freedom, so this is only considering torsional motions of a system like a powertrain. This translator uses a standard library, standard Modelica library, plus an additional Romax library that's supplied with the software. So in the example in front of you, you can see a relatively simple gearbox in this case that has then been translated using DynamicFUSION into this multi-body form here. And from there, we automatically and very quickly get a Modelica block which contains the information about the gearbox, and we'll see an example of this later. Inside that block are each one of the bodies that you see represented in the DynamicFUSION model here are represented by a block within this gearbox block. As I mentioned right at the start, the other translator that we have is to MSC Adams. Again, this is a very popular software, but this time Adams, of course, is a 3D software, or more specifically a 6D software. It includes all the deflections and rotations of a model. And again, the process starts the same in that we translate the model into the generic multi-body model, but then from there the translation is different, but again very fast, happens almost instantly, this translation into an Adams format. And this is a basic Adams format that can be read by all of the whatever Adams licenses you have. This is only using Adams View. So if you have Adams View, which is the basic level of Adams, then you can import a Romax model, but it will also work in other models, in other formats as well. If you want to include flexible bodies, as they're called in Adams, i.e. this is in Romax, this would translate, to example, to FE components representing housings and shafts and so on, then these can be translated too, but for that you need an additional Adams license, which is Adams Flex. But again, all degrees of freedom can be used, and we'll see an example with Adams later. As well as these two translators, you can also simply store the model as it is, the discretized model, so the converted model from the Romax model into the DynamicFUSION multi-body representation. And this is stored in the form of an XML file, which is very, very well documented. It's human readable, is easy to interpret using other pieces of software. And basically this means users can essentially write their own translators to their own software. And this is precisely what Gamma Technologies have done in creating a translator. They're in the process of creating an automated translator from DynamicFUSION into their GT Suite software, which we'll see when we look at the case study number 2 later. So summarizing the benefits of DynamicFUSION, we can build and edit multi-body models much faster than before because we're using dedicated software like Romax Designer or Concept, which are designed for building these models. And we can create multi-body models, again, very quickly in just a few seconds, that run faster without losing accuracy. We are reducing errors in creating multi-body models and effort by using the same model that many of you will already be using in Romax Designer for NVH analysis, for durability analysis, for efficiency analysis. We can reduce development time by identifying these problems early in the design phase as we possibly can. Even with a relatively basic concept model, we can still get useful information from a multi-body simulation. So very early on in the design process, we can start to look at multi-body simulation, transient dynamics, which typically in a sort of a current process may only be left right till the end of the design as a design verification, at which point it's too difficult and sometimes to iron out those problems. As well as part of this sort of right first time approach, we can see the effect of design changes very easily simply by changing the parameters in the Romax model, re-exporting the model using DynamicFUSION and simulating again. It's very quick and easy to do that. So we can see as the design changes, as the Romax model changes, you can see how your these non-linear transient failure modes that can only be simulated in a multi-body context, see how they behave as your design evolves. You can also, of course, by using this, you're making better use of your expensive multi-body software. If you've spending a lot of money every year on using Adams, then you want to be using it as much as possible for making engineering decisions and doing simulations, not really for the building the models. So by speeding up that part of the process, you're making more use of your Adams or Modelica investments. Excuse me. Because you're spending more time simulating and less time actually building the models. And of course, finally, this allows you to integrate your Romax software further into your design and development process to give you a sort of a smooth transition across the design and development process. So as I said, there's more information on our website. You can see, if you really want to, you can see a video of me talking about DynamicFUSION and see a demo on the website. Please go and do that. Now we're going to move on to the case studies and have a look at those. So the first case study is on gear rattle simulation, and we're going to be looking at a 5-speed manual transaxle gearbox, so pretty much a standard layout, but we're going to be looking at neutral idle rattle, and how we can simulate that using DynamicFUSION and both Adams and Modelica. Yeah. So we're going to show you how we convert the Romex designer model into the multi-body model using DynamicFUSION. And then we've got a one-dimensional, i.e. a torsional-only model, which we're then going to translate to Modelica and to Adams using DynamicFUSION. Typically, a one-dimensional torsional model is sufficient for rattle-type problems. And then we'll look at a simulation, and we're using here Daimler as the way of simulating Modelica. It's our implementation of Modelica we use here, and of course using MSC Adams as well. So now you can see the gearbox that we're going to be simulating. It's running in a neutral gear, as you can see, so the output is not turning, the input shaft is turning, and you can see that the wheel gear, the output gear of first gear here and second gear here are both rotating. So if we have an excitation coming in from the engine here, caused by engine firing, vibrations, this is what can lead to rattle in these two gears here in the first and second gear. So here's the model as it's converted using DynamicFUSION. So it's come straight out of Romax. We can open it up in DynamicFUSION, create the DynamicFUSION multi-body model. In this case, we have done the discretization phase. We've asked for a model valid up to 1000 Hertz, and this then chops the model up into appropriate sized and shaped bodies and connects them together with the appropriate stiffnesses and so on. And this is what you see here. Each of these brown discs represents a different body, and they're connected together by the connections that you see. The blue lines that you can see here represent the flexible body of the housing. You can see they're linking here the bearings together, and that will give us all the dynamic behavior of the housing included in the model as well. In this case, that's not particularly important because we're looking at a torsional only model, but obviously if you're looking at other phenomena, then that may be critical. So the size of this model is 130 degrees of freedom, and the time it takes to generate this model in DynamicFUSION is just 15 seconds. We can then translate that model to Modelica format, and here you can see a Modelica model. It's actually a pretty simple Modelica model, but it's enough for our purposes. The gearbox, this gearbox here, is actually all the information is contained in this block here. This is the output from DynamicFUSION that you see in Modelica. It's a block, Modelica block containing that. You also get another block here, and this determines the power flows. This tells you in which gear you're in. I can input a number here, first, second, third, fourth, fifth reverse. This block then is in a table which allows you to select which clutches, which synchros are engaged in the model here. And we've got a simple controller controlling the speed here, and you'll see what we're going to do with the speed in a minute. That's just a simple controller to allow us to drive the system, and we can view various outputs on these sensors that we've looked at here. So we've got an input here, and we've got two output sensors here, one on the first gear and one on the second gear. When you open up that Modelica block representing the gearbox and have a look inside, you can see why it's necessary to have something like DynamicFUSION. As soon as we move to these higher frequencies and we need this higher level description, you can see this model is now pretty complex. Each one of these dots here is another block representing each of the masses within the model, and obviously they're all connected together by various stiffnesses, also by gear meshes. Some of these links will be gear meshes, some will be synchronizers, and so on. So you can see just how complex these models can get. So to look at the rattle behavior, what we're doing here is we're going to drive the input at a particular velocity. We start at 0 and we ramp the velocity up to a particular rotational speed, and then once we've reached a certain speed, we start inputting a vibration into the system to simulate an engine vibration coming in to the gearbox, and we see what happens with the gear rattle. So the blue line here is the input. So we've ramped up to a particular speed, 80 radians per second here, and then we start exciting it here. The two lines here are showing the speed on the output gear of first and second gear. If you remember, in our gearbox, first and second gear are the two gears that are idling in this layout under a neutral condition. And you can see that, as you would expect, as the input ramps up, the outputs ramp up too. These gears, speed of these gears increases as well. And then when we switch on the excitation at the input, we're also starting to get a vibration coming through at the first and second gear. And what we're interested in seeing is if there's rattle behavior going on here. So when we zoom in here on the first gear, we're looking here at the velocity of the first gear output gear, the wheel gear. You see this shape of curve. Obviously it's following this vibration pattern that you saw coming from the input that we've put into the input shaft, but additionally you can see here it's not a smooth curve. At various points here, here, here and here, you can see the velocity is not smooth, it goes constant. And what that indicates when the velocity is constant is that there are no forces acting on that gear at that particular moment, i.e. it's not in contact with the other gear. It's moving about in the backlash region of the gearbox. And every time it leaves contact, you see the velocity becomes constant there. And we can see a similar thing for the second gear as well. We see a similar sort of behavior here. The easiest way to see the effect of that is to look at the displacement of each of the gear meshes. So this is the rotation of actually at the gear mesh, rotational displacement at the gear mesh. And you can see that you have this oscillating pattern. The upper limit here represents the gear in contact on the driving flank. You can see it starts off there before we start the vibrations. That's the driving flank where it's been turned, and then as we initiate the vibration, suddenly it loses contact on this side of the gear, this side of the backlash, and flies across the backlash region and impacts on the other side. And you can see this sort of bouncing behavior as the tooth impacts. And then as the excitation switches back in the other direction, we get the gear flying back the other way. So we're seeing this rattle behavior, and we're seeing how it bounces when those impacts occur. So we could now go back, and with this model we could make changes to it. We could make changes to our clutch design, for instance, or flywheel design, changes to the engine excitation signal in an attempt to reduce this rattle behavior. Now let's look at the same thing in Adams. We started from exactly the same point, except now our Adams model looks like this. Again, it looks similar to the model that you see in DynamicFUSION, with the flexible body here represented by this mesh here of the housing, but all of the other components you can see here: input shaft, counter shaft, and differential. Again, we see the similar behavior. We're doing pretty much the same thing. We start at 0 speed, we ramp it up to a particular running speed, and then switch on the excitation that you can see here, and again we get a response in the first and the second gears. Again, if we look at it, we see that similar behavior here with the regions of constant velocity indicating where we have gear teeth losing contact and rattle occurring. Here you can see a video of the model being ramped up, animating. You won't see the vibrations at the end because the scale is not big enough, but you can see that it's behaving as we would expect. As we start up the input shaft here, you can see the two gears here representing the first gear and second gear driven gears are also spinning up there. Okay, so let's summarize case study 1. We've got a Romex designer model of a 5-speed transaxle, converted to a multi-body model using DynamicFUSION. We've then translated that into both Modelica format and Adams format. We've applied a representative engine vibration to each of those models to see if there's any rattle behavior going on. We've done the simulation, and critically, we've got the simulation runs very quickly, despite a relatively complex gearbox model. So we started from a complex gearbox model. We've done the discretization to make it accurate to the level we requested, and then we've done the simulation, and all of that is just a few minutes work in total. So let's look at case study number 2. Here we're going to be looking at drivability simulation using GT Suite. As most of you will know, Romex technology is a market leader in the simulation of gearboxes and drivelines. And similarly, Gamma Technologies is a market leader, particularly well known in the world of engine simulation, but also with its GT Suite software moving into the world of driveline simulation as well. So this synergy is clear that there's a good for Romex and GT to be working together. And that's exactly what we're doing. We're looking at sharing simulation data between our software products, and that's going to give users of both of our products the best efficient collaborative solution, which encompasses the best of both worlds for the gearbox and the engine. And we're going to illustrate the hard work that's being done by Gamma Technologies and Romex here by looking at a drivability simulation. And this is using an engine model from Gamma Technologies coupled to a gearbox model from Romex Designer, and looking at the whole thing within the context of a complete vehicle driveline. The gearbox that we're looking at is a dual clutch transmission, and you can see the Romex model here. And to get the model into GT Suite, they require lots of data. You need to have the CAD data, which is exported using CAD Fusion, and this is for visualization purposes. And then also the multi-body model coming from DynamicFUSION, which is of course our main interest today. But both of those things are then used in the creation of this model in GT Suite. This currently is in the process of being developed by Gamma Technologies. It's approaching completion, and at the moment it is not fully automated. There's some manual intervention needed, but it's pretty much automated, and by the time it's finished it will be a complete automation, allowing you to go direct from DynamicFUSION into Gamma Technologies GT Suite. And you can see the example of the gearbox that's been created here from this multi-body model. So to look at the driveline drivability simulation, we need a complete driveline model. So we've got an engine model here. We're using a 1.5 litre petrol turbocharged engine model from GT Suite. And of course we have the Romex model coming from Romex, translated via DynamicFUSION into GT Suite. And as well as that, we need to be able to drive the system. So we've also got a vehicle model here representing the driveline and the vehicle inertia and drag coefficient and so on. But we also need to be able to drive it. So there's an engine controller linked to a transmission controller here, sort of electronics and hydraulics there. And there's also a controller to simulate the driver behavior. So when we run that through the GT Suite simulation, we get a result that you can see here. Here we're looking at a simulation from drive-away and acceleration through the first 3 gear shifts. And when we talk about balancing simulation time and accuracy, this is where you really start to see the benefits of that, because we've got a model that has the minimum number of degrees of freedom that we need for this particular example. And it's been optimized by DynamicFUSION for that reason. And this means that the simulation time is very fast. We're looking at about 3 times real time here for our simulation speed, which is very good for this kind of modeling. So we've got 3 curves on the graphs here. This is simply showing vehicle speed, the lower side, and we've got the vehicle acceleration, front to back acceleration, which is part of your drivability metric here in red, and the engine speed in blue. So we start off at idle, and then we engage the drive, and the vehicle starts to accelerate. And then there's a period of constant acceleration before we shift gear, another period of constant acceleration, shift gear, and so on. And you can see the engine speed fluctuating as we go through that. When we zoom into that, one of those shifting events, you start to see events that those of you who are driveline engineers or gear shift quality engineers will begin to recognize. The engagement, we get these sudden changes in the acceleration as a result of the gear shift, and these are the things that the gear shift engineer will be looking to improve. And the improvements may come from the control system. In this case, this is an automated transmission, of course, it's a DCT. These improvements may come from making mechanical changes to the gearbox, changing inertias of components, this kind of thing. But either of those things can then be updated in the model. They can be resimulated very, very quickly, either by changing the mechanical parts of the transmission in the Romax model and exporting, or by changing the control systems in GT Suite changing the control system in GT Suite to make these improvements. So let's look at a final summary then. We've got a 6-speed DCT model created. We've exported that model from Romax Designer using CAD Fusion for the geometry and DynamicFUSION for the multi-body model. In this case, we're looking at a 100 Hz frequency model. The DynamicFUSION data is then translated using the XML format, the neutral format in DynamicFUSION, and then using a translator created by Gamma Technologies, brought into GT Suite for the simulation. The model includes not just the gearbox, but it's got an engine, it's got a shift map and a transmission control unit, it's got hydraulic actuation, it's got engine controller, driver controller, and a model of the vehicle as well. We were able to simulate the drivability very quickly at 3 times real-time speed, and we're able to do this despite having a relatively complex system like a dual-clutch transmission. And we've also seen that the results are consistent with what we expect from this kind of simulation, and that we're able to identify common drivability metrics in the data that can be used to make changes to the design to improve it. So finally, to sum up, DynamicFUSION is used to create optimized multi-body models directly from Romax Designer and concept models. We can translate those models into Modelica format, into Adams format, or user-defined translators can be created by users using the neutral XML format. This means we can simulate nonlinear behavior like, for example, gear rattle as we've seen today, but many others as well. And we've also seen how Gamma Technologies and Romax are working together, and how we can use our combined efforts of our powerful simulation tools to simulate this detailed driveline behavior. We've looked at the complete driveline dynamic performance, in this case drivability. We can assess those using the combination of these 3 tools, Romax Designer, DynamicFUSION, and GT Suite. And so by linking the world's transmission and engine simulation together using DynamicFUSION, this is giving us a significant step forwards to an integrated right first time process for the complete driveline. Thank you very much for your attention, everybody.
Thank you very much, Michael. I hope you found our presentation useful and informative. Now let's begin our question and answer session.
Well, the first question is DynamicFUSION a module of Romax Designer? The short answer to that is no, it's not. It's obviously, it works with Romax Designer. It also works with our concept software product, for those of you that are familiar with that. And it's actually a separate standalone piece of software, so it doesn't have to be installed on the same computer as Romax Designer or concept. You can simply pass the Romax files or the concept files to DynamicFUSION and load them in like that. You can actually also launch DynamicFUSION directly from Remix Designer or Concept, which will then take you straight to the software, but that isn't necessary. So it's actually a completely separate product. Okay, we've got one more question here. How does DynamicFUSION work out what I need in the multi-body model? Okay, that's a very good question. So the level of detail that goes into a multi-body model typically depends on the phenomena that you want to investigate, which in turn usually depends on the maximum frequency of interest. The higher the frequency you need to simulate, the more you need to break the model down into smaller pieces to represent that dynamic behavior. And in that respect, a multi-body model is no different to a finite element model, where of course as you go higher in frequency you need smaller elements. So this is done, I can't give you details of the algorithm because it's proprietary, but this is done using an optimization process which works out how many degrees of freedom you need, how to chop the model up, where those bodies need to be positioned, and how they are connected together. And it's a sort of a multi-step process, an iterative process that runs very quickly, so that in a few seconds we get this model that is optimized in terms of the smallest number of degrees of freedom and the simplest possible model that will meet the requirements of the frequency you specify. You also have some control over the level of detail of things like gears and splines and so on. You can choose whether to just have a linear model of the gears or to have a non-linear model. So for example, in our rattle simulation, we have to have a non-linear model of the gears because we're interested in the backlash and so on. So there is some user control, but largely the whole process is automated, which of course makes it much easier to use.
Unfortunately, that's all the time we have right now, but Mike will answer any remaining questions by email. If you have any questions on this webinar topic or require further information, please email marketing@romextech.com and we'll get back to you as soon as possible. You can also register for a webinar next month, Bearing Analysis, presented by Dr. Riza Jamaluddin, EU Operations Manager, on Wednesday 29th of April at 8 AM and 4 PM BST time. For more information, please visit the webinar section of our website for upcoming webinars. We'll also be sending emails with more information on our webinars shortly. We hope you'll be joining one of our future webinars soon. Thank you and goodbye.